Hello, everyone. Welcome to this session on Databricks Lakehouse Overview, and thank you for joining us today. My name is Astrid. I'll be your instructor today. I've been with Databricks since 2019, and I work on the curriculum development team. So my role here is to put together instructor-led and self-paced content for our customers, and I will be the main one presenting today. Along with me today, we have fantastic TAs who are going to help us out. They'll be answering your questions in the Summit platform. So hello and thank you to all of our TAs. So let's go ahead and talk a little bit about this session. There are 2 sessions that are being offered for free during this Data and AI Summit, and I want to make sure that everyone is in the correct session. So the first of those complimentary sessions is the Databricks Lakehouse Overview. That is this session. This course was developed for those of you who are new to the big data and AI space. So perhaps you're in a more traditional business management role where you're helping your team move to the cloud. Perhaps you oversee a data science team and your primary role is to make sure that business needs are met, but you might not have a technical background yourself. Or perhaps you're looking to change careers and you're brand new to this space and want to know more about big data and AI. If any of those sound like you or similar to you, this is a great course for you to take. Our hope is that you walk away from this session feeling comfortable to have discussions about and even come to decisions about how to best position your organization to make the most out of your data. In this course, we will start with the basics. So in the first half, we're going to take a step back from Databricks and just introduce you to concepts like data types, data formats, the key roles and abilities to look for when you're building out your data teams, the different ways that organizations today are working with big data. So for example, what is machine learning and how does that differ from deep learning? We'll spend a good time talking about data management systems, so looking at the pros and cons of data warehouses and data lakes, for example. And we'll talk about the issues that organizations face when it comes to big data and AI. So that's the first half of the course. In the second half of the course, we'll review how the Databricks Lakehouse Platform fits into an organization's big data architecture. We'll talk about what it is, what it does, and then we'll review some customer case studies so that you can see how real-world customers are using the Databricks Lakehouse Platform to streamline their big data and AI needs. Everything we cover in this session will be from a business or operational perspective. So to be clear, we won't be showing any code in this course, and we won't have any hands-on technical labs in this course. So if you're sitting there and thinking, oh, I actually wanted something more technical, please look for the Lakehouse with Delta Lake Deep Dive course. That course is also complimentary this year, and it'll provide you with an in-depth look at Delta Lake features and functionality. In that course, you'll learn about applying software engineering principles with Databricks, and we'll demonstrate how to build an end-to-end OLAP data pipeline using Delta Lake for both batch and streaming data. That course will also discuss serving data to end users through aggregate tables and Databricks SQL analytics. So again, if you're looking for a more technical engineering course, that is the one for you. But if you're still here, I'm assuming that you're ready to get started with this course, so let's go ahead and get started. So here's our agenda for the day. Our session will be about 3 hours long, including a few knowledge checks and several breaks. For the knowledge checks, I'll ask you to please type your answers in the chat. If you have questions about anything I present, please also use the chat as well to ask those questions, and our TAs will be there to answer those. For some of you, this might be your first session, so I just want to make sure that everyone is good to use the chat. And I also want to know a little bit about you, so please go ahead and let us know where you're joining us from today. So please put that in the chat. While you do that, I'll let you know that I'm joining you from the Orange County area in Southern California. So I'll give everyone a few more seconds to type into the chat just where you're from. It's great to meet all of you. Again, thank you so much for being here. Next, I'm just curious if you could please let us know what industry your organization belongs to. So go ahead and type that into the chat. I'll give you about 10 seconds to do that. So again, we're asking for what industry your organization belongs to. Next, if you know, this might be fun. So what is the total volume of data that your organization manages today? So go ahead and put that into the chat. Again, I'll give you about 10 seconds to do that. And again, what we're looking for is the total volume of data that your organization manages today. And then just so that we know a little bit more on our end, so what do you aim to learn during this session? So again, I'll give you 10 seconds. This is really just so that we know why you're joining us today and what you're hoping to get out of this session. So if you could just add what you aim to learn during this session in the chat, that would be great. So again, welcome everyone, and let's go ahead and get started with our session. So we'll start with looking at big data benefits for business, and I want you to think about this question. I want you to think about how well you know this customer. So if I tell you that we have a customer, he is a male, he's 35 years old, he's single, he lives in New York City, and he makes about $100,000 per year. What do you think would happen if his bank account accidentally transferred $5,000 into his account? Do you think he would give the money back? Or do you think he'd take the money and run? So just think about this for a few seconds. If anyone feels particularly excited about either of these answers, go ahead and put it in the chat. And when you do that, tell us why. So why do you think that he would either give the money back or run? Now, I'm sure that some of you are thinking, well, we can't really know. There's too many unknowns. Well, what if we had more data? So let me give you a little bit more information. What if I told you now that this individual is Darth Vader? Yep, so I'm telling you that Darth Vader packed up the Death Star and moved to New York. How would knowing this change your assessment of what would happen to that money? So just in case someone in this call has not heard of Darth Vader, he probably wouldn't care about the legalities of keeping money that isn't his. So how did knowing this change your original answer? Or did it change your original answer? Knowing more about our customer allowed us to really up the certainty on what decisions they would make in a given situation. Now, obviously, this is a simple example. It's just a little bit of fun. But think about this example on a much larger and much more complex scale. And that is why big data and AI are becoming very important tools for organizations today. As we'll discuss further, big data is the new norm when it comes to data. So if your organization is not currently prepared to successfully process that data or analyze that data, or if you're struggling, it's really important to find solutions that can help you. Databricks is one of those solutions that we'll talk about again in the second half of our course today. So let's take a look at these statistics. Today, 83% of CEOs say that AI is a strategic priority for their organizations. And then we look at this quote. Gartner predicts the business value created by AI will reach $3.9 trillion next year. On the other side of that, though, Gartner also predicts that through 2022, 85% of AI projects will deliver erroneous outcomes. In other words, they will fail. As you can imagine, this is a complex landscape to navigate, which is why we built this course. Over the next few slides, we're going to look at some of the reasons why every enterprise today wants to begin to leverage their data for AI. When you combine big data and analytics, you can answer questions to help you get to know, again, your customers better, your vertical better, your organization better, your products better. You can help protect your business and stay ahead of the competition. You can ask questions like, how are customers actually using my product? How are my products performing? Is our data secure? Are we keeping up with industry trends? We list several questions like this on this slide. I'm sure that you can think of others. And even though we've been keeping this at a high level so far, these types of questions are relevant across every industry. So right now, I'll just give you one example from each of the industries shown on this slide. These are actual use cases on Databricks, but this is in no way an exhaustive list. So if you're looking at the retail space, someone might be looking to use AI for demand forecasting to predict real-time demand in retail stores. If we think about media and entertainment, we might have a streaming platform that wants to use our data to predict which customers are at a greatest risk for churn, and then proactively take steps to prevent churn. Maybe they'll do things like improving personalized recommendations, for example. If we look at the health and life sciences, we have research organizations who might want to combine real-world data sets, massive data sets, with genomic data to identify biomarkers that have high probability of driving the onset of disease, for example. Then we have financial services. So we might have companies that look to detect and prevent fraudulent activities, things like money laundering, credit card fraud, etc. They would leverage techniques like machine learning, for example, to predict anomalies in real time. So those are very different use cases, but they're all made possible as long as you're using the right tools on your big data. So before we continue talking about big data, let's just define what it is. And first, I really want you to think about how much data has changed over the last 20 years. And either in your head or in the chat, try to answer these questions. So, how has data changed over time? How has that affected what we can do with it? How has that affected how we manage it? Again, please type answers into the chat if you'd like. If not, just think about these for a few seconds. I'll give you about 10 seconds. So, over the last 20 years, advances in technology have completely changed the world that we live in. Today, the amount of data being generated every second has increased dramatically, and that's due to the invention of new sources of data that didn't exist before. Almost everything we do generates data. If you think about the things that you've done today, did any of you text someone or post something on social media? Did you exercise and log your workout using a fitness tracker? Have you used a smartphone today to browse the internet or pay bills or go shopping? At a minimum, you logged into the Summit platform to take this course. And as you did all of these things, you, along with the machines or the tools you use to do them, generated data. We typically think of data as being human-generated, machine-generated, and organization-generated. Human-generated data is data that humans create and share. So some examples of human-generated data can be social media posts, emails, spreadsheets, presentations, audio files, video files. I will stop here and point out that social media has been a leading force in the propagation of human-generated data. Just think, every time you post a message, change your online status, you upload an image, even when you like or forward a comment, you are generating data. Then we have machine-generated data. That is data coming from machines that don't rely on active human intervention. So some examples of machine-generated data sources could be sensors on vehicles, sensors on appliances or industrial machinery. What about security cameras, satellites, medical devices, personal tools such as smartphone apps or fitness trackers? And you might be asking, well, what does it mean for data to be generated without active human intervention? So if you think of a fitness tracker, depending on the model you have, it might generate records for your heart rate, your geographic location, the calories you burn, and more. You don't tell your fitness tracker to track these things. It comes programmed to do it, and then it does it on its own. And then we have organization-generated data, and that is data generated as organizations run their businesses. So if we think of some examples of organization-generated data, think about the records generated every time you make a purchase at an online or a physical store. We have things like unique customer numbers, the items you purchased, the date and time you purchased the items, how many of each item you purchased. This type of data, this organization-generated data, is often referred to as transactional data, and you'll hear that term frequently in the world of big data. Here's an example of transactional data. As you can see, we have a customer number, the item they purchased, the date and time they purchased it, and the amount they purchased. And one quick note here is that although all of these sources are constantly generating data, not all of the data generated is necessarily considered big data. So if you think of yourself sending text messages throughout the day, for example, the collection of your daily text messages is probably not considered big data, unless you're sending millions of messages, of course. Over time, those messages might be considered big data. So we've referred to this term big data for a while now, since the very beginning of the course. Now we'll actually define it. We'll review characteristics of big data. So let's start off by just looking at characteristics that distinguish big data from just regular, plain, normal data. One thing that is important here to note is that these characteristics, and why we're talking about this, these characteristics are what make it really difficult to work with big data, and why equipping your teams to do that work is not an easy task. So when we think about big data, that term big data refers to data that is nearly impossible to process using traditional methods, because there is so much of it coming in so quickly and in so many different formats. We summarize these major characteristics used to define big data as volume, velocity, and variety. Now, depending on who you're talking to, these V's, this volume, velocity, variety, can change. Sometimes there are other ones that people use to describe big data. In this course, we'll just stick to these three. I think it gives a pretty comprehensive overview of what we're talking about. So we'll start with volume. Volume refers to the incredible amount of data being generated every second of every day. The International Data Corporation, also known as the IDC, is a global provider of market intelligence. They do advisory services in the IT space, and they forecast that the amount of data that exists in the world will grow from 33 zettabytes in 2018 to 177 zettabytes by 2025. Just to put that into perspective, the computer I'm on right now has about 256 gigabytes of storage, and that's equivalent to just 0.00000000256 zettabytes. That was 9 zeros. 33 zettabytes seems like an impossible number. But if you think about how much data each and every one of us generates every day through social media, through cell phones, personal fitness trackers, etc., it starts to make more sense. If we look at this from a business perspective, that's great, right? We have so much more data coming in that we can use. However, how are you going to store that data? How are you going to capture that data, right? These are some of the questions that we start thinking about. The second characteristic that defines big data is velocity. And velocity refers to the speed at which new data is generated and the speed at which it moves around. So again, if we look at the IDC, they tell us that in 2025, each connected person will have at least one data interaction every 18 seconds. I mean, even now, think about the speed at which credit card transactions are checked for fraudulent activities. I know it's happened to me that I might be trying to purchase something out of the ordinary, and all of a sudden my credit card company reaches out to me within seconds to ask me if it was me. Sometimes it's so quick that they actually block the transaction right there until I verify that it is me. And while it's awkward to have your credit card declined, I'd prefer that to a stolen identity. From a business perspective, how can you make use of data coming in so quickly? And then also, how do your teams process such an enormous amount of data that is coming in both so quickly and then constantly? And finally, when we talk about big data, we have to talk about data variety. There's so many different types of data that are being generated today. We have social media posts, credit card transactions, biometric data, customer transactions, geographic information, and that's just to name a few. And it makes it really difficult to make sense of all of that data together. So again, if we put on our business caps and think from a business perspective, we ask ourselves, how can I combine all of these disparate types of data to extract useful information from them? We also mentioned at the very beginning of this course that there are different types of big data. And as you can imagine, different types of big data have different storage and processing requirements. Today, we'll talk about these three main types of big data that I have on the slide here, which are structured, semi-structured, and unstructured data. Every data science team today, including those in your organization, are probably using all three of these. And as mentioned, each of them require varying amounts of processing before they can be used to generate business insights. So structured data. The term structured data refers to any data that conforms to a certain format or schema. It's usually clearly organized, and so because it's clearly organized, it's generally easier to analyze, which is why for a long time, we kept our data as structured data. If we look at this spreadsheet, for example, we see that there are clearly labeled rows and columns, and the information within those rows and columns follow a schema. So for example, the customer ID seems to be a 5-digit numerical value. The title of the movies are all letters and numbers followed by parentheses. Genres are also separated. So let's go from structured data to unstructured data. Unstructured data does not follow or fit neatly into a schema. It's often referred to as messy data because it isn't easily searchable compared to structured data. Because of that, this data is typically the most difficult to analyze. Of course, it's also the most widespread type of data. The IDC reports that almost 90% of data today is unstructured. And because unstructured data is so readily available, it can be really valuable in terms of extracting meaningful insights for your organizations. One of the most powerful aspects of machine learning, for example, is that we can use it to analyze this type of data. So again, in the chat, I'll give you about 10 seconds. Can you add in some examples of unstructured data that you might be working with? So any unstructured data that you have coming into your organizations or that you'd like to use to help drive business decisions, go ahead and type those into the chat. And we're seeing some of this come through, but yeah, some examples of unstructured data can include social media posts. We have photographs, videos, emails, audio files, video files, images, the list goes on. Then we have semi-structured data. So semi-structured data fits in between structured and unstructured data. Semi-structured data does not reside in a formatted table, but it does have some level of organization. What we have on the screen here is JSON. You can see that our data is tagged, but the number of tags could vary. So in this particular example, we have middle name or salary or birth date. So we've covered the three types of big data. Again, structured, unstructured, and semi-structured. And of course, due to the characteristics we just talked about, we can't use traditional methods of computing to handle this data. So now we'll pivot a little bit and take a quick look at how we process big data. How we process that big data is called distributed computing. I'll explain this by using an example that we use a lot when we talk about distributed computing. I'm sure it's something that you're all familiar with. I know I am. But you might have had a situation as a kid where you and your classmates were asked to guess how many pieces of candy were in a jar. And the person who guessed the correct number got to take that whole jar of candy home, eat candy for days. Sure, your parents were super excited about it. But imagine this. What if I gave you and a group of your colleagues an entire tub of candies? So not just a jar anymore, but a large tub of candies. and I told you that whoever finished counting the candies first was going to win some sort of prize. The caveat here is that the count has to be accurate for you to win. You have to be spot on. So what would you do? And as we're talking through this, just think about what you would do. If you would like to, please go ahead and post your answer in the chat. This might be fun to see what different people would do. And actually, let's go ahead and do that. So I'll give you about 30 seconds. Write an answer in the chat. The question again is, if I gave you and a group of your colleagues an entire tub of candies and told you that whoever finished counting the candies first wins a prize, what would you do to count that candy, to win that prize? So go ahead and type something into the chat. So I'll start highlighting some of these ideas, but you might line the candies up and count them one by one. And that would eventually give you an accurate count, really accurate, fantastic, but it would take a really long time, right? If we have thousands of candies, you're going to be counting for a long time. You could also weigh the candy. You could weigh one candy and then weigh the entire tub of candy somehow and figure out how many pieces of candy there are based on those weights. Now, that would give you a count relatively quickly, but I never told you that the candies were the same types of candy, right? So what if there are different types of candy in that jar? Then you can't guarantee that all of the candy weighs the same, so you might not have an accurate count. Now, if we look at this differently, we can have our colleagues help us, right? So what if we split up the entire tub of candy between our colleagues? We can distribute the candies among all of them so that instead of us having to do the whole count on our own, our colleagues are all counting candies at the same time, and that will obviously help us get through that tub of candy much faster. And that idea is the idea behind distributed computing. So you take data, you divide it into small chunks, and you distribute it among workers, which are just different computers. We can then perform whatever our computation is, in this case, it would be a count, in parallel on smaller subsets of data. Distributed computing is what makes it possible to process big data. So for those of you who have heard of Apache Spark, or maybe you haven't heard of Apache Spark is the de facto standard when it comes to distributed computing tools used for big data processing and big data analytics. The founders of Databricks are actually the ones who invented Spark. And for years, Spark has been the core engine underlying Databricks. When we think in terms of big data processing, there are two types of data that we process. So we can process batch and streaming data. And those terms, batch and streaming, refer to the way that we're getting our data and the speed at which we're getting our data. So batch data. Batch data is data that we have in storage and that we process all at once, or we process in a batch. So say, for example, that someone gives you a large jar of candies and asks you to count all of the candies in that jar. That is an example of a batch job because you take those candies that were already present in some form of storage, in this case, a jar, and you are going to count them. Since you count them all at one time, that is considered a batch processing job. A real-world example of batch processing is how telecommunication companies process cellular phone usage each month to generate a monthly bill. So to do this, they process batch data, the phone calls you've made, the text messages you've sent, etc., any additional charges you've incurred through that billing cycle to generate your bill. They process that data in a batch job. On the other hand, we have streaming data. Streaming data is data that is being continually produced by one or more sources and therefore must be processed incrementally as it arrives. So going back to our candy example, what if instead of counting candy sitting in a jar, we're asked to count candy coming towards us on a conveyor belt? As the candy reaches us, we have to count the new pieces and we're constantly updating our overall candy count. In a streaming job, our final count is changing in real time as more and more candy arrives on the conveyor belt. So, a real world example of stream processing is how heart monitors work. All day long, right? You wear your heart monitor, it receives new data, dozens of thousands of data points per day as your heart beats. Every time your heart beats, new data is added to your heart monitor in real time. If your heart monitor has a display of your average heartbeat for the day, then that average will be constantly updated with the new numbers from that incoming stream of data. And both batch and streaming data have their place when it comes to big data analytics. So batch data is used for things like periodic reporting. Streaming data is used for things like fraud detection, right? That's something that needs to be identified in real time. We can go back to our credit card example, right? And I mentioned that sometimes you purchase something that might be out of the ordinary and instantly your card is blocked. So historically, it's been difficult to use these different types of data in conjunction. Thanks to new advances in technology, however, combining batch and stream processing is possible. And you can imagine that leads to significant advantages in big data analytics when you can combine those two. So next, we're going to ask if anyone has any questions before moving on to what big data looks like in organizations today. Before doing that, we'll take a 15-minute break. So please take a look at the time right now, and we will meet back in 15 minutes. I'll give you a reminder when we have 10 minutes left and another reminder when we have 5 minutes left. See you soon. All right, we have 10 minutes left of our break. And here's your 5-minute warning. We have 5 minutes left on our break, and then we'll go ahead and get started again. So let's pause now and ask if you have any questions. Please remember to drop any questions into the chat so that our TAs can answer them. At this point, we have defined big data. We've looked at characteristics of big data. We've also talked about how we process big data. And now we're going to move into more of the big data analytics and looking at techniques that organizations use to analyze data. There are some terms that are thrown around quite a lot, sometimes interchangeably, and we want to start off by looking at some of these terms. We'll review the relationship between artificial intelligence, machine learning, and deep learning. Like I said, a lot of the times these terms are thrown around, but they do mean different things. So let's go ahead and start reviewing these terms. Artificial intelligence. In essence, artificial intelligence is a branch of computer science in which computer systems are developed to perform tasks that would typically need human intelligence. Artificial intelligence is a broad field, and there are a lot of subcategories, which we'll talk about in a couple of minutes. To contextualize AI, let's look at a classic example, which is a Turing test. The Turing test was developed by Alan Turing back in 1950. It essentially tests a machine's ability to exhibit behavior equivalent to human behavior. In a Turing test, a human evaluator asks a question using a text-based medium to both a human and a machine without being able to see either one. If after a preset period of time, the evaluator is unable to determine which responses are coming from the human and which are coming from the machine, the computer is said to have passed the Turing test. And it's an interesting thought experiment, right? Can we create a computer that can act so human-like, that an actual human just can't tell? So far, there are no uncontested results where a computer has passed the Turing test, but some scientists are predicting that this will change in the near future. But now we'll talk about some specific subfields of artificial intelligence, particularly machine learning and deep learning. Machine learning is, like I said, a subset of artificial intelligence. The goal of machine learning is to learn patterns in your data without explicitly programming a computer to do it. So there are a few types of machine learning. I'll list them off just in case you hear these terms so that you're familiar with them. There's supervised learning, we have unsupervised learning, reinforcement learning. The most commonly used type is supervised machine learning. And that is where you are given a set of data with the correct results already labeled. And the goal is to predict the labels or the outcomes of new data of that same format. So let's go into a fraud detection example, for example. Without machine learning, people would manually specify rules for what constitutes fraud. So this could be the number of transactions per month. Maybe if the number of transactions per month are more than 20, right, that might be fraud. An average balance. Maybe if you have less than $100, that constitutes fraud in these rules. These rules are brittle though. They're prone to human error. They can quickly go stale. With machine learning, you can create an algorithm though with an input data set that contains transaction information that has already been labeled as fraud or not fraud. After the algorithm is created on that data, you can pass in new transaction data that has not been labeled as fraud or not fraud, and the algorithm can predict if the data is fraudulent. So is this fraud? Is this not fraud? And that can be extended for millions and millions of transactions. So here again, we see that power of big data. You can process far more data than any single human analyst can. And you can detect changes in trends as new types of fraudulent activity emerges. You should still include a human in the loop. They are the ones that will manually investigate and verify the model's predictions and make sure that if the model is saying something is fraud, it actually is fraud. Aside from machine learning, we also have deep learning. While our supervised learning example is very good with tabular, that's structured data, so for example, data that's in a table or an Excel sheet, we also have deep learning. Deep learning performs well on complex data sets, things like images, sequences, or even natural language. Deep learning is a subset of machine learning that uses something called neural networks, which were inspired by the structure of the human brain. They're much more complex than most machine learning models, and they require significantly more time and effort to build. Unlike machine learning, which plateaus after a certain amount of data, deep learning continues to improve as data size increase. Deep learning is expanding into more and more domains, things like generating movie scripts, predicting cancer based on MRI scans, and making anyone feel like Van Gogh with style transfer. So let's think about an example using images. Let's say that we want to build a model to classify if an image contains a koala or a panda. So if you were to describe a koala, what would you say? It's small, it has fluffy ears, it has a large oval-shaped nose, it has small beady eyes, and that's all true, and that helps us differentiate koalas from pandas. But what if your image of a koala is very zoomed in? What if it's zoomed in to a point that it doesn't have a left ear? Does that still make it a koala? Machine learning and deep learning solutions need to be robust enough to detect changes like this. If you show a human child an image of a panda and a koala, odds are that they can distinguish between those two really well just based on the examples we talked about, right? The large oval nose and the short fluffy ears, etc. To train a deep learning model to distinguish between those two, however, requires lots of examples and lots of time. Deep learning models learn differently from humans. So when we look at deep learning models, the model might be looking at features like patterns in the fur or the shape of the eyes, etc. So over time, the model learns what a koala is and what it isn't, and it's able to make decisions quickly based on that information. So we'll pause here a second and I'll ask, and go ahead, put this in the chat, but can anyone think of any examples of artificial intelligence or machine learning that we use pretty much all the time? Go ahead and post some examples in the chat. Again, I'm giving you 30 seconds to do this. Just think about what you either experience, maybe what you witness day to day. AI and machine learning, they're really prevalent. A lot, I think, more than many of us are aware. So I'll just give you a few more seconds to type your answer into the chat. Just any example of AI or machine learning that you're aware of. So some examples are recommendations. Online shopping centers. Whenever you see those, based on your shopping cart, you might be interested in this, or based on what you watched, you might be interested in this. There's one example right there. Fraud detection. We've talked about this a little bit already, but financial institutions using AI to teach computers or have computers teach themselves what constitutes fraudulent activity. What about facial recognition? Social media sites or your phone? Have you ever been on a social media site and you get a tag that says, hey, this is you in a photo, or this is your friend in a photo? So we've talked about artificial intelligence, machine learning, deep learning. Where does data science fit into all of this? So data science is a field that combines tools and workflows from disciplines like math and statistics, computer science, and business. And those tools and workflows are used to process, manage, and analyze data. So data science is very popular in businesses today as a way to extract insights from big data to help inform business decisions. How does data science relate to the techniques we just talked about? Well, machine learning, deep learning, artificial intelligence, those are common tools in a data scientist's toolbox to help extract insights from data. What we've talked about so far is not an exhaustive list. These are some of the most popular techniques for working with big data, however. An important idea to note here is that one of the benefits of using these techniques, particularly machine learning and deep learning, is that they really help scale analytics. We've mentioned this already, but as you can imagine, once machines learn how to detect patterns in our data, they're able to make predictions much faster than human can, and at a much larger scale. So as we discussed, all of these techniques are used by data science practitioners to help extract insights from big data. They use these techniques as part of a data science workflow, and that's a series of steps they follow to process, manage, and analyze data. And we'll actually take a look at the data science workflow now, because now that we've established a difference between AI, machine learning, deep learning, data science, we should talk about what your data teams are doing or what they can do with these frameworks. The reason why we're going into the data science workflow, I think it's important that we just chime in and let you know, why are we talking about AI? Why are we talking about the data science workflow? So when it comes time to make a decision as to what technology or set of technologies you need to equip your teams with, or when it comes to creating a big data organizational strategy, it's important to understand what it is that each member of your team does, because ultimately your choices are going to affect how they work. And I know this is probably true of a lot of people here. I know I've had this experience in the past that your manager purchases a tool. It's supposed to help you do your work more efficiently. Sometimes they purchase these tools and you had no input. They didn't ask, right? There was very little communication with you. And when you start using the tool, you realize it actually doesn't help you with everything you have to do. Now you're left scrambling to try to figure out how to make up for the workflows that the new tool doesn't cover. And what's more, if it's not compatible with tools you already use, then you might have an even bigger problem. So again, let's start talking about this data science workflow. And this is the workflow that individuals on data science teams will typically work with as they're working with big data. The steps in this data science workflow can be broken down into identifying business needs, ingesting data, preparing data, analyzing data, and then sharing those data insights. So let's talk through each stage and why it's needed. Identifying business needs. So this is typically the first step in the data science workflow. It's the first step that we'll discuss. In this step, you typically have a business leader, a manager, for example. It might be you in your organization. You come up with a list of questions that you want answered. Questions like, should we make changes to our product? Which of our customers are at the greatest risk for churn? Why are they at the greatest risk for churn? Maybe questions like, can we save money by changing the way that we're pricing our products? In this phase of the data science workflow, managers or business leaders are, again, identifying a set of questions or business goals that data practitioners will work to solve or will work towards. In the data ingestion phase, your organization is taking data in. There's often a combination of different types of data. So you might have real-time data, which comes in streams. For example, a customer transaction that gets added to your data store every time a customer makes a purchase. You might have the continuous data from a heart monitor or a fitness tracker. And other times you'll have data that's ingested in batches. We just talked about this a few minutes ago. So chunks of data are being imported to your data store at one time. An example of ingesting batch data could be loading customer records into your data store that might exist in spreadsheets somewhere else, maybe on someone's local drive, for example. At this stage, at the data ingestion stage, data is often raw, it's often messy. Then we go into this data cleansing or data preparation stage. After your organization ingests raw data, it needs to be prepared for use through a deep cleaning and preparation process that's often referred to as data munging. Munging data can mean anything like cleaning it up, extracting data, standardizing data, joining, consolidating, or even filtering data. The point here in the data cleansing and preparation stage is that you're preparing data enough so that people using it to, for example, train a machine learning model or generate a dashboard or a business visualization don't have to fix their input data or don't have to spend a lot of time fixing their input data. Then we have this data analysis phase. During that data analysis phase, your teams are exploring this prepared data. They want to find insights. Oftentimes, this is where machine learning comes into play. Again, although machine learning isn't the only type of data analysis that can be applied to your data, it's becoming more and more popular today, especially in conjunction with big data. Aside from machine learning, individuals can also query data, produce visualizations, etc. Then we have this sharing phase, sharing insights. So once those business insights are discovered, they're often shared back to you if you're a manager, perhaps another stakeholder, who are going to use them to make business decisions. And that data is typically shared through an interactive dashboard. It might be an email, it might be a presentation, etc. So at a high level, this is what your data science teams are doing with that big data. Now we'll take a closer look at the individuals doing these things. So who is responsible for what? As we go through this section, just think to yourself, does my team look like this? Especially in smaller companies, we've seen situations where one person is fulfilling all of these roles. But we do want to point out that these are highly specialized roles, and as businesses grow, they they trend towards breaking out these roles into a variety of skill sets. Some organizations will break these roles out even further. But again, for the sake of this session, we just want to show you an example of these roles. And these are the roles that we see frequently in the organizations that we work with. So let's start off with data engineers. Data engineers develop, construct, test, and maintain data pipelines. Data pipelines take data from its raw data source and they move it along to where it can be used at different stages of a data analytics or a machine learning project. You can think of data engineers as sort of your first line of defense. They're the ones that are taking that raw, messy data and performing data munging. To perform their duties, they use a set of tools to build and maintain those pipelines. That can be anything from programming languages like Python or Scala, different data storage solutions. They will also have different processing engines. So for example, Apache Spark. Data scientists then take that data prepared by data engineers and they'll use a variety of methods to perform analytics. Data scientists typically have a strong background in disciplines like math or statistics or computer science, and they often are tasked with building machine learning models, testing those models, and then keeping track of their machine learning experiments. To perform their duties, they will use tools like, again, programming languages, Python, R, SQL. They'll use machine learning libraries, and they'll use notebook interfaces. So if you've ever heard of Jupyter, for example. Then we have data analysts. So data analysts also take that data prepared by data engineers to extract insights. Typically, a data analyst will also present data in the form of graphs, it might be charts, dashboards, to stakeholders to help them make business decisions. Data analysts can also take advantage of the work of machine learning engineers to help derive insights from data. They're typically well-versed in data visualization tools and business intelligence concepts, and are often in charge of interpreting data insights and effectively communicating those findings with their stakeholders. To perform their duties, data analysts often use SQL. They'll also use visualization tools like Tableau, Power BI, Looker, and others. We also have platform administrators. Platform administrators, sometimes they're called DevOps engineers or infrastructure engineers, maybe cloud engineers, but a lot of the time they end up responsible for managing and supporting big data infrastructure. So that can be things like setting up your organization's big data infrastructure, updating, maintaining, and performing health checks on that infrastructure, and also providing governance to data science team members around changes or upgrades to that infrastructure. To perform their duties, platform administrators often use tools like the various infrastructure and monitoring services, that major cloud providers offer. And that helps them keep data secure and also scale and manage their infrastructure. So while I was going through this, I asked you to think about, does this match with my team? Does this seem familiar? And again, we'll post in the chat. I want to know, are we missing any roles? Can you think of anyone on your data science team that doesn't fit neatly into one of these roles? So go ahead and type that into the chat. Maybe this aligned well with what you see in your organizations. Like we mentioned, sometimes you have people who do more than one thing. So just curious to see what those roles are and how this aligns to what you're seeing in your organization. So thank you to everyone typing those answers into the chat. And now we will pivot and talk about something that we've probably all run into, or at least the data practitioners on our data science teams have certainly run into, which are some of the challenges working with big data. This is an important section because it really helps set the stage for why Databricks was built in the first place. Throughout this course, we've made reference to, big data is difficult to work with. There's a lot of different types and they have to be stored in certain ways. So in this section, we'll dig into that a little bit deeper and actually give you examples of what we mean when we say that organizations have significant challenges working with big data and AI. To kick this section off, I just want to ask you a question because I'm sure this is something that everyone on the chat is familiar with. It's probably why you're in this session. What are some of the challenges you've seen organizations face when it comes to big data? Big data processing, big data analytics. Think about that question. Again, write your answer in the chat. I'll give you about 30 seconds. As you're writing in the chat, I'll give you some ideas. So maybe you've seen that even though your team members know what they're doing, they're really talented, they're really smart, there just isn't enough of them to scale. Right? So you see some of these answers coming through. There might be so many tools that you can use that you don't know where to start. So thank you to everyone posting their answers in the chat. Now, in the early days of data analytics, simple relational databases, historical data, and spreadsheet expertise were used to drive business decisions. And with the emergence of big data, these methods are no longer sufficient. Today, businesses are spending a large portion of time and resources trying to piece together solutions for how to extract insights from big data. And we already talked about this, but close to 90% of organizations are failing. So why is this? Well, challenge number one. We've said this multiple times, working with big data is not easy. It's very difficult to manage, right? So we've talked about data coming in massive volumes, faster than ever before, in a wide variety of formats. And as data practitioners work to design their organization's big data infrastructure, they're trying to answer questions like, where are we going to store all of this data? How are we going to store all of this data? How are we able to process batch data with streaming data? How can we use different types of data together in our analyses? So what if I want to combine unstructured data with structured data? And then how can we keep track of all of this work that we're doing on our big data? As you can imagine, there are many ways that an organization can set up big data infrastructure, and getting it right is not easy. What frequently ends up happening is that organizations will set up different technology stacks to handle their data workloads. And often these technology stacks don't work well together due to many different tools introduced that are not compatible or not easily compatible with each other. You might have proprietary data formats that are not easy to translate from one tool to another. And if you want to enable advanced use cases, you might have to move across these stacks. So think about the work your organization does. You probably don't have a data warehouse use case, right? Or a streaming use case. You probably have a supply chain logistics use case, or maybe it's a financial risk assessment use case. So to address those challenges, you need to move across these technology stacks. We also have siloed roles that lead to inefficiencies. So when we have these multiple stacks set up, these multiple technology stacks set up, many organizations suffer from the challenges of having siloed functional roles for individuals on their data science teams. What do we mean by that? So it's not uncommon for a data scientist to build and train a machine learning model in a vacuum on their computer with little to no visibility to related work being done by, for example, a data engineer who's preparing that data for them, or a data analyst who might be using the results from their experiments to produce dashboards. And so that ultimately leads to communication slowdowns. You might have teams, and this is really common, that you have teams working with different versions of the same data. This also leads to data security issues and governance issues, and ultimately, you will have a less productive data team. And we talked about this a little bit, but definitely want to pull out data security challenges as its own section here, because if we go back to, we've referenced Gartner a few times in this session already, but according to Gartner, 80% of organizations will fail to develop a consolidated security policy. That leaves them and their data vulnerable to breaches, security breaches. And think about the ramifications of a security breach. Beyond just the immediate monetary cost, there's a long-lasting loss in customer trust and company reputation. This has happened to me. If you've ever been a customer of a company that has suffered a security breach, you know firsthand how long it can take to rebuild trust. Plus, besides protecting data from just leaking out, organizations also must ensure that they're compliant with data protection regulations. We have things like GDPR, so the European Union's General Data Protection Regulation. We have the Health Insurance Portability and Accountability Act, or HIPAA. And one of the biggest issues that organizations face, and we have referenced this, and this is, again, in addition to these siloed roles and different technology stacks being put together, security breaches, etc., is collecting and storing data. It's incredibly complex, as you can imagine, with data volumes increasing, data is becoming more distributed, data types are changing. Setting up and maintaining a big data infrastructure to manage all of that data is very complex. And that's why today, many organizations struggle with their data storage systems, particularly figuring out which technology is right for them and where to migrate their data to. In this session today, we'll take a look at data warehouses, data lakes, and the lakehouse. And the lakehouse is the way that Databricks looks at the world. And we'll get to why in just a few slides. But first, let's start with data warehouses. So data warehouses have been around for about 30 years. And if you work for a data-driven organization, it's really likely that you're using a data warehouse now to power your company's decision-making. Data warehouses evolved as a set of guidelines to design systems that controlled the flow of data used in decision-making. And in many companies, they delivered immediate benefits by reducing the duplicated data found in isolated data marts. Data marts which had been developed for use by a single department within the company, and that contain highly specific views of data used to then generate reports or guide business decisions. The problem is that if you have many departments that need similar views of data, and if you work for a large company, you might have dozens of data marts with almost identical data. But then you have different naming conventions. You might have different update frequencies. And those redundancies lead to high costs for storage and development and maintenance. And there's also confusion, right? When you're trying to refer to data that isn't managed by a central set of rules. The data contained in data warehouses comes from a variety of sources, generally referred to as operational data, and that's data that can be anything that drives the functioning of a company. So things like point of sale systems or customer relationship management systems or even inventory management systems. By combining data from diverse sources into common tables, analytic insights can be used to drive that decision making. So while glancing through a database or a spreadsheet can provide a quick glimpse into the behavior of a given account, for example, a data warehouse is going to give you the ability to drill down and look at seasonal trends in, for example, how a subset of products have performed with a specific customer in mind in various regions. But why can't we generate reports like that from operational databases? For example, how a product is performing with an enterprise customer in a specific region. So that really boils down to the design and the intent of those systems. BI reports, as you're well aware, can often take minutes. Sometimes they take hours to generate results. And data warehouses are designed to optimize those queries. They are optimized to prevent conflicts between concurrently running queries. And data warehouses make the assumption that the data that is entered is unlikely to change with high frequency. So that's why if you aggregate results over millions of records, data warehouses assume that those records will not change while they are being processed or while they're being accessed. Now, let's go back to the retail point of system. So imagine a retail POS or a point of sale system, for example. There are new sales that are constantly being processed. And it's often the case that a recently completed transaction might need to be invalidated. It might need to be updated. Let's say that a customer notices a discrepancy on their receipt. Trying to run a report on that type of system might result in inconsistencies in results. It could prevent users from making updates until a report is finished. Now think about the front end, how frustrating that would be for a customer and how expensive that would be to a business if a salesperson is not able to complete their transaction or process a return anytime an analyst runs a query on the back end. So that's where data warehouses come in. Data warehouses help keep your operations running smoothly because they collect data from these various systems, your point of sale systems, your customer management systems, in a process called ETL or ELT. That's extract, transform, load, or extract, load, transform. Basically, there's a team of data engineers and database administrators, and they define how data from different systems will be processed and stored. They design that process so that BI analysts can then count on data in that data warehouse to be clean, it's validated, they know that it's being updated on a consistent basis. And that kind of ETL workload, that extract, transform, load workload, is vitally important to business operations. Any delays or errors in those processes can lead to delays in reports or inconsistent reports, etc. Now, one thing to note here is that data warehouses were originally developed using on-premises technologies. So there have had some pain points when it comes to adapting to the modern data atmosphere. We talked about this several minutes ago, but the proliferation of smart devices, the proliferation of web-based commerce, for example, has really increased the volume and the variety of data. Data warehouses traditionally relied on proprietary data formats. That means that they often do not support videos or images or free text files. And traditional data warehouse technologies force customers to invest in enough compute power and storage to handle your peak user traffic. So as you can imagine, as companies have seen this exponential growth in their data in recent years, that kind of design can become extremely expensive. So then we have cloud-based data warehouses, and they have addressed some of those challenges. Because of the flexibility of the cloud, it's always possible to scale up the amount of computing power or the data storage that you need. That being said, Many data warehouses still use compute-attached storage. So that means that scaling up and down is not that easy. If you need to scale down the size of your compute and storage, for example, that can be difficult. So cloud-based data warehouses, a pro is that you don't need to buy or maintain the right number of physical servers in order to scale up. But you may find that your recurrent cloud costs are growing exponentially alongside of your data because of that connection to the compute-attached storage. So another big point for data warehouses, and it's important we talk about this one, is that they don't have native support for machine learning applications. The databases and the tables that are used in data warehouses aren't well suited to working with unstructured data, things like user comments, things like images. We've talked about this in this course. And data warehouse vendors generally don't allow outside applications to directly access their proprietary data formats. Now, machine learning algorithms, we've talked about this, they need access to huge amounts of data. Neither the way that the data is stored in a data warehouse, nor the query engine in a data warehouse is optimized to return the data needed by data scientists. In addition, the open source technology that powers a lot of machine learning applications can't actually communicate natively with those proprietary data warehouses. So we've talked a little bit, let's take a pause here. We've talked a little bit about the pros and the cons of data warehouses. Next, we will talk about data lakes and how they evolved to address some of those issues. They've come into widespread use over the last decade. Data lakes are often defined in opposition to data warehouses because while a data warehouse delivers clean, structured data for BI analytics, a data lake allows an organization to essentially store anything they want cheaply. When we look at data warehouses require knowledge of what data will be used and how it will be used before any kind of engineering begins. With a data lake, though, those decisions about how to use data can be delayed by months or even years and then uncovered later. This process is known as data mining. So that process of analyzing these large amounts of historical data and then figuring out what are we going to do with this? Maybe you uncover patterns or you find some anomalies that may have predictive power. That is a core building block of many successful machine learning applications. Data lakes originally evolved as an on-premise technology. They were closely tied to the Apache Hadoop ecosystem. I'm sure many of you are familiar with Hadoop. Many early internet companies had been amassing these huge amounts of data, and they were seeking solutions to process that data and monetize that data. That's where the Hadoop Distributed File System, or the HDFS, came in. That allowed engineers to start working with data distributed across dozens or hundreds of servers as if it were part of the same machine. So what that meant is that physical infrastructure was still expensive to purchase. They still had to purchase computers, maintain those, update those as well. But that ability to work with data distributed across dozens or hundreds of servers as if it were a part of the same machine is what allowed these big companies like Facebook or Netflix or Yahoo to create and power these new data-driven applications. There are a lot of companies, in fact, your company might be one that continues to run HDFS data lakes on premises, but most companies have transitioned to working in the cloud or are in the process of transitioning to work in the cloud. Each of the cloud vendors offer their own take on object storage. It's particularly well suited for use as a data lake. And there's a number of reasons for that. So the first is that object storage doesn't rely on the same relationship between compute and storage seen in a traditional file system. So if you break this down a little bit, think about a file on your laptop. When the laptop is turned off, there's no way to gain access to that file system and load the contents, right? It's off. With object storage, any computer that has the unique address for the data and the right security privileges, of course, can access it no matter where they are. So that means that any number of computers can write to and read from that shared object storage simultaneously. And they don't need to worry about running these expensive computing resources in order to keep that data available. The best part is that there's no upfront investment in infrastructure or in contingency planning for lost data because all of that is provided by the individual cloud vendors. And while prices are obviously going to vary by cloud and the specific terms of a contract or your agreement will vary by cloud, you are going to see a huge decrease in monthly cost typically. So usually the monthly cost is around 2 cents per gigabytes of data, so it's extremely cost effective. Now, a huge point here, and something that is the opposite of a data warehouse, is that data lakes have the benefit of supporting any kind of data, regardless of structure, regardless of format. As we mentioned before, that's very important for running machine learning applications. In a data lake design, data storage and compute are not coupled. And so there are a number of technologies that have evolved around working with data stored in that type of way. Apache Spark is one of those technologies. It is the compute engine used by Databricks. One thing to note, and this is an important distinction between data lakes and data warehouses. A data warehouse is a specific technology supported by a vendor that's built around a proprietary format and a query engine. A data lake is more of a service model for delivering data. Regardless of the location of the data lake, the end user has a number of options for the compute engines that can process that data efficiently. And data will be stored in open formats, and that makes the migration of that data simple. So it sounds like data lakes came around. They are the solution to the traditional data warehouse. However, for all of their strengths, they have not completely eliminated the need for data warehouses. For BI analytics specifically, most companies continue to load the relevant data from their data lakes into a data warehouse. And it's in that data warehouse that analysts execute queries and generate reports. So let's look at this a little bit closer. Here is a diagram that represents a common pattern we see in the field. So you have data from numerous sources landing in a data lake. A lot of that data will be stored here indefinitely, waiting for the organization to figure out what to do with it later on, perhaps for use in an ML application, machine learning application. An ETL pipeline will load some of that data from the data lake into a data warehouse. And in that data warehouse is where the quality of that data is checked, and analysts can have that confidence that that data is ready to be used to derive insights. Data scientists who want to work with this data have two options at this point. They can either go back to the data lake and implement new logic to check and enforce the quality of that data, or they can run additional ETL jobs to get data out of the data warehouse back into an open format, so then it can be used in machine learning. And that probably sounded really convoluted and confusing, but that's why neither of these options is ideal, because it leads to a lot of data redundancies and a lot of additional engineering work. It also means that there could be delays in data freshness, or even a reduction in data quality. What we see today is that many companies, and this might be true in your company, choose to use both a data lake and a data warehouse in their architecture. And I do want to be clear that when we're talking about data lakes and data warehouses, we are relying on two assumptions here. One is that you have a data lake that is implemented using standard open source formats without transactional processing. We're also assuming that data warehouses are relying on data storage in a proprietary format on an attached storage volume. That attached storage volume is also known as block storage. So if you remember, maybe 10, 15 minutes ago, we described object storage. Object storage is that cheap cloud storage that allows data lakes to remove compute costs from storage costs. So the decoupling of that compute and storage. Cloud vendors will also offer block storage. That is similar to if you think about renting a portable hard drive in the cloud. So you might be able to change the computer that the hard drive is connected to, but unless a machine is powered on and running the right software, it's not possible to get your data. Some cloud data warehouses have adapted a hybrid model. And so you can actually leverage object storage to cheaply store your data that you use infrequently. And then you would only load it into the more expensive block storage when you need it. We also have some vendors that have gone one step further, and they allow direct querying of data stored in open source formats in a data lake. And this does solve some of the issues with data warehouses. Again, it does not provide an answer for those machine learning workloads or working with truly unstructured data like an image. At Databricks, we approach this issue a little differently. So we've created the idea of a lakehouse, essentially combining the best of both worlds. So the data reliability and governance that you get from a data warehouse, but also that flexibility to store and work with different types of data and different formats that come with a data lake. We'll review more about the Lakehouse as we dive into the Databricks Lakehouse Platform. So before we move on, I've done a lot of talking. I want to make sure people have the chance to ask questions. Please make sure that you're asking your questions in the chat so that our TAs can answer those for you. I also want to do a bit of a knowledge check here because we have talked about big data. We've talked about ways to store that big data, ways to analyze that big data. So I'm going to go ahead and ask you a couple of questions here. I'm going to read off some comments that you've probably heard in the past. And then in the chat, I'd like you to come up with why these statements either make sense, great, good to go, or they do not sit well with you. So again, please post your answers in the chat. So statement number 1, in the long run, scaling up our existing on-premises infrastructure will be less expensive since we'll own the machines. So go ahead, does that sit well with you? Do you think that's a fair statement? Do you have any issues with that statement? And if you do, please go ahead and let us know why you have an issue with that statement. You can go ahead and add that into the chat. I'll give you about 10-15 seconds here. So again, in the long run, scaling up our existing on-premises infrastructure will be less expensive since we'll own the machine. Go ahead and type your answers or continue to type your answers into the chat. So I'm going to say that's not sitting well with me. I think about the cost of owning a machine. I'll have to maintain it. I'll have to make sure that they're upgraded from time to time. Anytime there's new software that comes in, I'll have to make those updates. As technology changes, etc. I have to get staff now to maintain and secure those machines, especially I'm not going to have one. I'm probably going to have several or dozens of machines. So I'm going to say this one is not sitting well with me. The next comment you hear, to help streamline our workflows, we should make sure that the technologies staff are using are compatible with each other. So again, does that sit well with you? Go ahead and let us know in the chat. I think this one's pretty straightforward. To help streamline workflows, absolutely, you do want the technologies that staff are using to be compatible with each other as much as possible. What about this one? To ensure data protection, it's a good idea to invest in independent technologies that each specialize in a specific part of our data workflows and can each be protected separately. So think about that one. That's an interesting question or an interesting statement. So go ahead and type your answers into the chat. Again, that is to ensure data protection. It's a good idea to invest in independent technologies that each specialize in a specific part of our data workflows and can each be protected separately. So as your answers come in, I'm going to say that's not necessarily a good idea. Because if that's the path you choose, then you have to deal with different tools, different methods of security, trying to coordinate users between those tools. And in this course, we did talk about those siloed technology stacks. The more tools you have, the more you have to think about whether they're compatible to each other, for example, how to get them to talk to one another. So great job on that. Now let's do a little bit of review when it comes to data lakes and data warehouses. I'm going to read a list of descriptions. You tell me And you can post this in the chat or just sit there at home and think about this. But tell me if the description describes a data lake or a data warehouse. So if we're thinking about a technology that is compatible with unstructured data, think about it. That would be a data lake. Congratulations to those who got that correct. What about the ability to hold any amount of data at a low cost? So this technology can scale to hold any amount of data at a low cost. That again would be a data lake. What about the user interface of this technology is familiar to users of traditional databases? The user interface is familiar to users of traditional databases. That is going to be a data warehouse. And then one last one, which of these is typically associated with vendor lock-in? So that means that your data resides with them, with the vendor. All right, that one is going to be a data warehouse. Yep. Data warehouse associated with vendor lock-in. Okay, great. So let's go ahead and move on. We are getting to the point of the course now where we have talked about the big data benefits for business. We've looked at big data characteristics. We've looked at big data types, big data processing. We talked about batch data. We talked about streaming data. We've talked about artificial intelligence, machine learning, other types of analytics that are used in analyzing big data. We looked at the data science workflow and the roles on a data science team as they take big data through that data science workflow. In this last section, we looked at some of the struggles with big data and AI that many organizations are facing. We took a look at what happens when you have siloed technology stacks, siloed roles on your data science teams, some issues that organizations face with data security and making sure that you're being compliant with laws like GDPR, making sure that you have the right security certifications you need to run your businesses. Now we're going to switch over and start talking about Databricks. The moment has come. So in our next session, we're going to take everything we've learned so far to help us understand what Databricks actually is, what that Lakehouse platform does. And then again, we'll take a look at some real world customer examples, customer success stories of customers that are using Databricks. Before doing that, we'll take a 15-minute break. So please take a look at the time right now, and we will meet back in 15 minutes. I'll give you a reminder when we have 10 minutes left and another reminder when we have 5 minutes left. See you soon. All right, we have 10 minutes left of our break. And here's your 5-minute warning. We have 5 minutes left on our break, and then we'll go ahead and get started again. Okay, so we're back, ready to talk about Databricks and the Lakehouse Platform. Databricks is the data and AI company. It makes big data and AI easier for organizations to manage. And the whole point behind what Databricks is and what we want to help our customers do is enable that data-driven innovation in every enterprise. A simple way to describe the Databricks Lakehouse platform is that it empowers everyone on a data science team to work together in one secure platform from the minute that data is ingested into an organization through when it's cleaned up, when it's analyzed, and when it's used to inform those business decisions. So the Databricks Lakehouse platform will allow organizations to ingest, process, and transform big data, massive quantities and types of data, explore data through data science techniques, including but not limited to machine learning, for example. It will also guarantee that data available for business queries is reliable and the most up-to-date data an organization has. It also provides data engineers, data scientists, data analysts, the unique tools they need to do their work. And it helps and we've talked about this, but it helps organizations overcome those traditional challenges associated with data science and machine learning workflows. And that's what we will explore in detail in this lesson. So how this works. So basically, data practitioners access Databricks functionality using a custom-built web-based interface. This is an environment for accessing all of your Databricks assets. So things like notebooks, you might have libraries, you might have dashboards, for example. And on top of accessing all of those assets that you're using day to day, or that data practitioners are using day to day, it also is how you will access the computational resources you need to process your data and to process those queries. So while you might be using different tools or functionality within the Databricks Lakehouse platform, depending on your role, everyone is working in one platform, and that's key. So here's an example of one of the user interfaces you can use when you're using Databricks. This is the Databricks workspace. When you log in, this is what data practitioners will see, and then they'll use different functionality based on their roles. Another concept we want to bring up now, and this is specific to the Lakehouse, is that the data in a Lakehouse is in an open format. Databricks invented some of the most successful open source projects in the world. You can see those in this image here, and we continue to contribute to those projects regularly. When your organization uses Databricks, you're getting managed access to those open source data projects through the platform. Plus, you are unifying your big data system with open source standards. And by aligning to open source standards, you're basically establishing building blocks that help make your applications more interoperable with different systems. So here's a conceptual image of the Databricks Lakehouse platform. What you see here is that we have different types of data coming into the platform. We operate across the major cloud vendors. If you have questions, please let us know in the chat. So we have all of this different type of data coming into the platform. That's structured, semi-structured, unstructured, and streaming data. And that data is landing in an open data lake. On top of that data lake is Delta Lake. So you see this logo here, Delta Lake. We'll talk about Delta Lake in a few minutes. On top of Delta Lake are these use cases, including things like data engineering, BI and SQL analytics, real-time data applications, and then, of course, your data science and your machine learning use cases. So we have two ideas to really unpack here. The Lakehouse, which is at the heart of this platform, and Delta Lake. As we mentioned before, Lakehouse is this new open data management paradigm, and it combines the most popular capabilities of data lakes and data warehouses. Per their design, they implement similar data structures and data management features to those in a data warehouse, but they do that directly on the kind of the low-cost storage used for data lakes. So when you merge these ideas into one single system, it means that data teams can move faster because they can use data without accessing multiple systems. And teams also have the most complete and up-to-date information or data available for these different use cases. Lakehouses have the following key features. So they have transaction support. That means that multiple parties can concurrently read or write data. They have data schema enforcement that helps ensure data integrity. So if you have a right to a table, for example, that right will be rejected if it does not match the table schema. Lakehouses also come with governance and auditing mechanisms to make sure that you can see how data is being used. And there's also BI support. So BI tools can work directly on source data, right on that freshest, most reliable data, and that really helps to reduce data staleness. Huge factor here, and we've talked about this, so the idea that storage is decoupled from compute, that means it's easier for your system to scale to more concurrent users and to different data sizes. This idea of openness. So storage formats used are open, they're standard, plus there are APIs and various other tools that make it easy for team members to access data directly. And there's support for all data types, structured, unstructured, semi-structured, streaming, etc. There's end-to-end streaming with the Lakehouse. So real-time reporting and real-time data can be integrated into data analytics processes just like existing or batch data is. We also talked about Delta Lake. And so now let's talk about the relationship between Delta Lake on Databricks and a Lakehouse. That's a question that we get a lot. It's really key to understanding what it is that the Databricks Lakehouse platform does and how these components fit together. So first off, Delta Lake was developed at Databricks. It was open source in early 2019. And Delta Lake on Databricks is a term that we use for the managed version of Delta Lake that comes with the Databricks Lakehouse platform. So I'm just going to refer to it to Delta Lake, but I do want to make that distinction. With Delta Lake, you are bringing structure and governance inherent to data warehouses to data lakes. And that is what creates the foundation for a lakehouse. When data practitioners use Delta Lake, they tend to follow this architecture pattern that consists of organizing data that's ingested into your organization into successively cleaner tables, starting with this idea of a bronze table, moving into a silver table, and then stopping at a gold table. We're going to dive into this just a little bit. This won't be a super technical discussion, but it is important to understand what's happening on the back end because the way that data is organized using Delta Lake affects how your downstream users in your organization will interact with and use that data. So we start with this bronze table. This bronze table contains raw data ingested from various sources. It can be IoT data, for example. Maybe they're JSON files, for example. Data in those bronze tables are often kept for years. This is what we talked about, that an organization can keep it in that table for years until they decide what to do with it. That data is kept as is. So in other words, it's kept in its raw state. Then we move into a silver table. A silver table is going to provide a more refined view of your organization's data. That data, this data in a silver table, is directly queryable and ready for big data and your AI projects. Data in that silver table is often joined from various bronze tables. That's done to enrich records. It can be to update records based on recent activity. But data in the silver table is clean and it's normalized. And this is what we refer to as that single source of truth. We also talked about the idea of data marts. Goal tables are going to provide that business level aggregate used for your particular use cases, for example. Goal tables are what are going to provide the business level aggregates used for particular use cases. So for example, if the sales department for an online retailer needs to create a weekly dashboard for a specific set of data every week, in that case, a data engineer can prepare this data for that department and include aggregations such as daily active website users. Maybe they include weekly sales per store. Maybe they include gross revenue per quarter for that department. The data stored in gold tables are usually related to one particular business objective. So there are several elements that are sort of housed under this Delta Lake umbrella. And what we'll review now are those elements. There's 4 of them. We have Delta files, you have Delta tables, the Delta optimization engine, and then you have that Delta Lake storage layer. So first up, we have Delta files. By design, Delta Lake uses Parquet files to store an organization's data in their object storage. Parquet files are a state-of-the-art file format for keeping tabular data. They're fast, and they're considered more powerful than traditional methods for storing tabular data because they store data using columns instead of rows. And all this means is that when you're querying, this columnar storage allows you to skip over non-relevant data very quickly. So your results are going to take considerably less time to execute. Delta files leverage all of the technical capabilities of Parquet files, so they're fast, but they also have an additional layer over them, and that layer is going to track data versioning and metadata, and it also stores transaction logs so that you can keep track of changes made to a data table or to an object storage directory, and it's also going to provide ACID transactions, which we'll talk about in just a little bit. So then we have Delta tables. A couple of things about Delta tables. So Delta tables are collections of data kept using Delta Lake technology. Those Delta tables will have Delta files that contain the data, your data, and kept in object storage. Tables are also registered in a metastore. A metastore being basically a catalog that tracks your data's metadata, so the data about your data. The Delta tables will also have that Delta transaction log that is saved with those Delta files in that object storage. Then we have Delta optimization engine. So Delta engine, it is a highly performant query engine. It provides an efficient way to process data in your data lakes, and it accelerates data lake operations and also supports a variety of workloads. Those can be large-scale ETL processing workloads. They can also be ad hoc interactive queries. And many of these optimizations just take place automatically. So you get the benefits of Delta engine capabilities by just using Databricks for your data lakes. What the Delta optimization engine means for your business is that your data workloads run faster. Then we have this Delta Lake storage layer. When using Delta Lake, your organization stores its data in a Delta Lake storage layer, and it accesses that data via Databricks. A key idea here is that an organization keeps all of this data in files in object storage, and it's beneficial because that means that your data is kept in a lower cost and easily scalable environment. So what we'll do now is review how Delta Lake guarantees reliable data. Part of diving into how Delta Lake brings this reliability and this governance to your data lakes requires going through some of the issues that organizations face with data lakes. So one thing with data lakes is that data can be hard to append. So what that means is that while it's easy to write data to a data lake from many sources and then read that data with many different systems, if you have an ongoing data job, you might need to write dozens or hundreds of files before a transaction completes. What can happen is that a query might capture a partially written data set, and then that can lead to invalid results. With data lakes, you can also have jobs that fail midway. So when you are updating a data lake, you might have numerous files that are written one after another. In that update, if for whatever reason that update fails after some of the files have been written, it's difficult to recover where you actually are. What is the correct state of that data? And oftentimes data engineers will spend countless hours troubleshooting failed jobs and trying to figure out what actually moved over, what is the valid state of this data. Something else, another challenge with data lakes is that modifying existing data can be difficult. So data lakes are designed to have data written once and then read many times. The concept of modifying or deleting data wasn't really of central importance at the time they were designed. But now with regulatory measures like GDPR, CCPA, for example, Companies have to be able to identify and delete a user's data if they request for that to happen, if the user doesn't want them to have their data anymore or use that data in a certain way, for example. We briefly touched on this when we talked about streaming data, but real-time data is difficult to leverage, even with data lakes. So many organizations struggle to implement a solution that will allow them to leverage their real-time data with their historical records. A lot of the time, that means that you have to keep multiple systems and multiple pipelines in sync in order to be able to do that. That can be expensive. It's also difficult to manage, and there can be some consistency problems that just take a lot of time from your data engineering teams. In addition, keeping historical versions of data can be quite costly in a data lake. Some industries have strict regulations for data reproducibility, and they require historical versions of data to be maintained. With the huge scale of data present in a data lake, it can be pretty expensive and difficult to archive all of this data for compliance. It's also difficult to handle large metadata. So we talked about this, metadata being the data about your data. If your organization has truly massive data, reading that metadata can often create substantial delays in processing and overhead costs because there's just so much of it. And then we have this too many files cause problems. So some applications will write small files out to data lakes, and over time, you might have millions of files that build up. When that happens, your query performance is going to suffer because there's a small amount of data that's spread over so many files. And then all of those files are being read just to get to that data. You also have data quality issues, and that will affect your analysis. So we've talked about this, but data lakes don't have built-in quality checks that data warehouses do. That's why we talked about SQL analysts moving their data from a data lake into a data warehouse. Queries against data lakes need to be constantly assessing data quality and anticipating possible issues. If the proper checks are not executed, that can be quite expensive. You might have long-running queries that fail, queries that produce meaningless results, etc. So right there, we just took a more technical dive into exactly what is going on when we talk about challenges with data lakes. And those are the biggest ones that we've seen when we work with customers in the field. So how does Delta Lake address those pain points? One of the biggest benefits, the most powerful benefits of using Delta Lake is that you get ACID transactions. It adds ACID transactions to your data lakes. ACID refers to a standard set of guarantees that most databases are actually designed around. Since most data lakes have multiple pipelines that read and write data at the same time, data engineers often spend a significant amount of time to make sure that data remains reliable during these transactions. With ACID transactions, each transaction is handled as having a distinct beginning and an end. That means that data in a table is not updated until a transaction successfully completes, and each transaction will either succeed or fail fully. So in other words, what that transactional guarantee does is it eliminates a lot of the motivations for having both that data lake and the data warehouse in an architecture. Appending data becomes much easier because each new write will create a new version of a data table, and that new data will not be read until that transaction completes. So again, if a data job fails midway, it's disregarded entirely. This also simplifies the process of deleting and updating records because many changes can be applied to data in one single transaction, and that eliminates the possibility of incomplete deletes or incomplete data updates. Besides ACID transactions, we also should talk about schema management. So Delta Lake gives you the ability to specify and enforce your data schema. It automatically validates that the schema of the data being written is compatible with the schema of the table it's being written into. So columns that are present in the table but are not in the data are set to null. And if there are extra columns in the data that are not present in the table, the operation will throw an exception. What that does is ensures that bad data that could corrupt your system is not written into those tables. And with Delta Lake, you can also make changes to a table schema and then apply that automatically. There's another concept of scalable metadata handling. With Delta Lake, metadata is processed just like regular data with distributed processing, which makes things a lot faster. Then unified batch and streaming data. We've mentioned this several times throughout this course. So Delta Lake is designed from the ground up to allow one single system to support both your batch and your stream processing of data. Those transactional guarantees of Delta Lake mean that each microbatch transaction will create a new version of a table that is instantly available for insights. So many Databricks users use Delta Lake to transform the update frequency of their dashboards and their reports from days to minutes, while eliminating that need for multiple systems. We also have this idea of data versioning and time travel. So with Delta Lake, the transaction logs used to ensure ACID compliance create an auditable history of every version of a table, and it indicates which files have changed between versions. That log makes it easy to retain historical versions of the data to fulfill compliance requirements in various industries, again, looking at things like GDPR and CCPA. So in summary, all of that functionality we reviewed helps organizations streamline these operations. They are improving their data pipelines. They are unifying real-time and batch data. They're enabling the performance of BI workloads directly on your data lake, and it's enabling you to meet regulatory needs. So Delta Lake and this Lakehouse platform allows your data engineers to make sure that all of the data being used by downstream users is that refined data that they need. When we think about the Databricks Lakehouse platform for BI and for SQL analytics, we have Databricks SQL Analytics that is a part of the Databricks Lakehouse platform. That is a SQL native interface that provides SQL users the ability to write queries in a familiar syntax and explore their organization's Delta Lake. Something really great about SQL Analytics is that regularly used SQL code can be saved as snippets, and so those SQL analysts can quickly reuse that SQL code. Query results can also be cached, and so that will keep the query shorter. Once queries are built, SQL Analytics also enables your data analysts to make sense of those results through a wide range of visualizations. Those visualizations can be organized into dashboards through a drag and drop interface. It's really easy to use. And those dashboards can be shared with other users to provide insights. They're also configurable, so they can automatically refresh and alert your team to any meaningful changes in your data. A key point here is that SQL Analytics was designed to work with Delta Lake. So you're getting all the performance optimizations, the governance, the reliability of that data in your data lake, but you're able to use it with the SQL native interface. Plus, the platform also supports existing BI tools. So if, for example, your SQL analysts have a preferred visualization tool that they want to use to query your organization's Lakehouse, they can use those preferred visualization tools. Then when it comes to the Data Lakehouse platform for data science and machine learning, data science and machine learning teams use the Databricks Lakehouse platform throughout the entire data science and machine learning life cycles. They use the platform to explore data, prepare and process that data, build and test machine learning models, put those models into deployment, optimize those models, etc. That is done through various platform components that we won't get into specifically or technically right now, but things like collaborative notebooks, the Databricks machine learning runtime. We have managed ML flow. We'll discuss those briefly here. So collaborative notebooks are web-based interfaces. They contain runnable code. They contain visualizations. They can contain narrative text. Those notebooks are used in data science and machine learning workflows to perform exploratory data analysis, to clean up data, to build machine learning models. They support multiple programming languages, so languages like SQL, Scala, R, Python. The machine learning runtime. This will provide data scientists and machine learning practitioners with scalable computing resources that come with built-in popular data science frameworks. We also should mention managed MLflow. That is built on top of MLflow, which is an open source platform developed by Databricks. That open source platform was developed to help data scientists and machine learning practitioners manage the complete machine learning lifecycle. With MLflow, you can track machine learning experiments, you can manage machine learning models, and you can also deploy those models. When data practitioners are working with the Databricks Lakehouse Platform, they're sharing tools found within the platform, but they're also sharing all of the assets that you create, anything that is created inside of that platform, whether they are machine learning models prepared by a data scientist, whether it's a dashboard prepared by a SQL analyst. Maybe a data engineer is working to ingest some data. He has some code or she has some code in a notebook that they want to share. Perhaps there's some data sets that are relevant to everyone on a team. All of those assets are shared with everyone working within that platform. So that has been a high-level overview of the Databricks Lakehouse Platform. At this point, basically everything we've talked about in this course has come together. So we started with this: what is big data? What are the structures? What are the types of big data? How is it processed? How do data teams work with it? What are some of the techniques used to work with it? And then we came into how all of those concepts are tackled with the Databricks Lakehouse Platform. What we'll do now is give everyone a chance to just look at some success stories from Databricks customers. Before we jump into those customer stories, let's do a knowledge check. So I'll post some questions here. Go ahead and answer them in the chat if you would. That would be great. Our first question here, and these will be about the material we just covered. So we'll be looking at Databricks and the Lakehouse Platform. So in which of the following stages of the data science workflow do organizations use Databricks for big data and AI? Data ingestion, data preparation, data analytics, or sharing data? So go ahead and type your answers into the chat. So the answer here is that organizations use Databricks for all of these stages of the data science workflow. Organizations and data practitioners within those organizations use Databricks from the moment that data is ingested all the way through that sharing data insights stage. All right, great job. Next question. True or false? The Databricks Lakehouse Platform comes with different user interfaces tailored to data practitioner roles. True or false? Go ahead and put your answers in the chat. So that's going to be true. And we actually covered a couple of those in this course so far. For extra points here, can anyone remember what those user interfaces were that we covered in this course so far? So one is the workspace, the Databricks workspace. There was one other one that we covered. That was the one that was a SQL native interface, Databricks SQL Analytics. Okay, next question. I'm curious if anyone can name some of the open source projects created by Databricks that you have access to via the Databricks Lakehouse Platform. I showed a slide several minutes ago and it had some of these projects on there, and we have talked about some of them, so I'm just curious. So which are some of the open source projects created by Databricks that you have access to via the Databricks Lakehouse Platform? All right, so let's share this slide again. Here's several of them. Apache Spark, Delta Lake, ML Flow. Qualas and Redash we did not talk about in this course so far, but those are some additional open source projects built by Databricks. Okay, the Databricks Lakehouse Platform is best suited for which types of data? So in this course, we've talked about several types of data. Go ahead and type your answer into the chat. The Databricks Lakehouse Platform is best suited for which types of data? And of course, the answer there will be for all types of data. So we've talked about unstructured, semi-structured, that structured data, and also streaming data. Great job, everyone. Let's keep going. Just a few more questions. What are some of the benefits that the Lakehouse brings to your organizations? So I'll give you a few hints here. One is transaction support. The other is BI support. This one might be a little tricky, but there was a slide I showed several minutes ago, and then we talked through some of these benefits. So go ahead and drop your answers or type your answers into the chat. So I'll bring this slide back up so that we can just take a look really quickly. So we talked about this transaction support, BI support. There's also that data schema enforcement. It brings that governance and that auditing capabilities to your data. This one's important. So if you remember, we talked about storage being decoupled from compute. Using storage formats that are open to make sure that your data and your system is interoperable with other systems. Then we just reviewed this as well, that support for all data types and this end-to-end streaming. All right, which of the following lays the foundation for your lakehouse? We have a few choices here: Delta Lake, Apache Spark, ML Flow, or the workspace. Which of the following lays the foundation for your lakehouse? Go ahead and add your answers to the chat. And the answer is going to be A, Delta Lake. Congratulations to everyone who got that one right. Delta Lake lays the foundation for your lakehouse. All right, one more question. Thinking about Delta Lake this time. So we talked about that Delta Lake architecture of landing data in successively cleaner tables. Which of the following tables is considered an organization's single source of truth? So your options here are bronze, that bronze table, the silver table, and the gold table. So go ahead and answer in the chat. And the answer here is going to be that silver table. We also talked about organizations potentially needing this business level aggregate data. Does anyone remember which table that type of data would be found in? Would it be the bronze, the silver, or the gold? It's that business level aggregate data. That would be that gold table. So it's taking data from that silver table and then setting it up and further refining it for those specific business use cases that typically have one objective tied to them, one business objective tied to them. All right, great. Thanks everyone for your participation. Next, we're going to take one more break. And when we come back from that break, we'll finish up the course by looking at 3 of our fantastic customers that are using the Databricks Lakehouse platform to streamline their big data and AI workflows. This will be a 15-minute break. One more 15-minute break, and then we'll finish up the course. All right, we have 10 minutes left of our break. And here's your 5-minute warning. We have 5 minutes left on our break, and then we'll go ahead and get started again. Here are some of the outcomes in a variety of industries that we've seen. Value can be quantified in terms of productivity gains, cost saved, revenue increases, etc. The results can be pretty dramatic, as seen here. And we'll also look at some numbers in the following customer examples. So we'll start off by looking at H&M. So H&M is a huge innovator in the fashion and the retail industry. They rely on data as the core for everything they do, and they have stores opening up globally at a really rapid pace. H&M needed to improve their supply chain and forecasting operations to streamline their costs and also maximize their revenue. They were working with an on-premises Hadoop system, and that older system was really crippling their ability to ingest and analyze data being generated by millions of customers. And they needed that data to power their predictive machine learning models. We're talking about massive volumes of data from over 5,000 stores in over 70 markets with millions of customers, and that's every single day. H&M wanted to make use of all of that data for AI. But again, that legacy Hadoop-based architecture was not sufficient for that. They just weren't able to scale to meet their business requirements. So at H&M, data engineering was challenged because they had a fixed number of computing resources that they could use. And they also had a complex infrastructure, which was really resource intensive. It was costly to scale, and they did suffer from some data security issues. Data sources were siloed, and that impacted the data science team's productivity. And because of all of that, it would take the data science team a whole year sometimes to go from model ideation to productionalization. So Databricks was able to address all of these challenges right out of the box. The Lakehouse Platform, as we mentioned, is a fully managed platform. It simplified managing those compute resources. It simplified infrastructure management and operations at scale. And this collaborative notebook environment, because it supports multiple languages, meant that a diverse team of users could work together in their preferred languages, which meant there was this unification across the team environment to fuel productivity. Now you can have the data science teams working with their data engineering teams, all working in their preferred language and all working in one place. When H&M moved over to Databricks, it improved their operational efficiency. It actually reduced their operational costs by about 70%. The Lakehouse platform dramatically reduced the number of components needed for data scientists and engineers to work together. And overall, this had a huge business impact with faster time to insight. So they had this ability to be more granular in their decision making. All right, we also have a Regeneron. Regeneron takes genomic data and they bring new medicines to patients in need. One of the issues Regeneron had was that they had poor processing performance and limitations when it came to scalability. And so their data teams could not analyze the massive amounts of data, of genomic and clinical data that they had. More than 95% of all experimental medicines that are currently in the drug development pipeline are actually expected to fail. To improve those efforts, the Regeneron Genetics Center built one of the most comprehensive genetics databases by pairing sequenced exomes and electronic health records of more than 400,000 people. And it was a massive, massive, massive data set. One of the challenges that Regeneron faced is that genomic and clinical data is highly decentralized. So it's really difficult to analyze or train models against, again, that entire data set. That was 10 terabytes of data. It was also difficult and very expensive to scale their legacy architecture to support analytics. Or with a 10 terabyte data set, they were looking at over 80 billion data points. They had data teams that were spending days just trying to prepare data so it could be used for analytics. Regeneron chose to use Databricks. They simplified their operations to accelerate their drug discovery. And it really improved, coming over to Databricks really improved their data science productivity. So some of the concrete outcomes. The Databricks Lakehouse platform reduced the time it took data scientists and computational biologists to run queries on their entire data set from 30 minutes down to 3 seconds, which is a 600 times improvement. ETL could be done in 2 days versus 3 weeks. And as you can imagine, lowering that overhead has enabled their teams to support a broader range of studies now. So instead of spending so much time just managing the overhead, they can now focus more on these projects that can help bring treatments and medicines to people that need it. And then finally, Comcast. So Comcast was working on a voice remote. Customers could ask the remote for personalized programming recommendations. As you can imagine, that is a huge amount of data. If we dig into this a little bit more, let's just think about what it means for a voice remote to work. So what happens is that the remote is instantly answering a customer's voice request for a particular program. It's turning billions of individual interactions into actionable insights. And that strained Comcast IT infrastructure and their data analytics and data science teams. On top of that, Comcast needed to deploy models to a disparate range of environments. So they had cloud, they had on-premises environments, and even directly to some devices in some instances. So they had some very specific challenges. Billions of events were generated by their entertainment system. They had over 20 plus million voice remotes. And so again, that's where that petabytes of data originated that needed to be analyzed. They had poor collaboration. So they had data scientists working globally and working in different programming languages. It was often difficult to share and reuse code, which added overhead and time to development efforts. And then the management of machine learning models, like I mentioned, they were developing, training, and deploying hundreds of models. It was very manual. It was very slow, difficult to replicate. And so it made it difficult to scale those models to millions of customers. Comcast moved over to Databricks. As I mentioned before, with the Databricks Lakehouse Platform, you have an automated infrastructure, and Delta Lake made it possible to create these more robust and faster data pipelines. With Databricks, Comcast built out these rich data sets to optimize their machine learning at scale. They streamlined their workflows across their teams. It improved collaboration, reduced the complexity of their infrastructure, and helped deliver this awesome experience to their customers. Delta Lake enabled them to optimize files, and that way they had a much faster and reliable ingestion of those files at scale, of that data at scale. So again, looking at the numbers, with Databricks, Comcast reduced their compute costs by about 10 times. Delta Lake enabled Comcast to optimize their data ingestion. It replaced 640 machines with 64, and at the same time, it improved performance. Now that means that team members spend more time on analytics and less time on managing all of that infrastructure. Prior to using Databricks, it would take approximately 5 full-time DevOps employees to onboard 200 users, and that dropped down from 5 to 0.5. Delta Lake also enabled the data team to use data at any point within that data pipeline created by their data engineers. That just allowed them to act more quickly when it came to building and training those models. And it was faster to deploy those models. So deployment times for models went from weeks to minutes. With that, we've come to the end of this session, and we'll leave you with this. So today, more than 5 billion customers interact with data every day. By 2025, that number will be 6 billion, or about 75% of the world's population, and that's coming from an IDC white paper. And by 2022, more than half of major new business systems will incorporate continuous intelligence that uses real-time context data to improve their decisions. This is coming from Gartner. So today, as we saw throughout this course, the promise of big data and AI has never been more achievable. Putting it into practice is another story that has never been more challenging. You know, the success of your organization's analytics processes hinges on knowing, one, the challenges that lay ahead so that you can avoid some of the common pitfalls that other organizations have faced. And then a huge one here is making sure that you're using the right technologies that can scale with your business. So we hope that you enjoyed this session. We hope that at this point you feel comfortable talking about high-level concepts related to the big data landscape. Just to wrap up here, in this session, we talked about big data benefits for business. We talked about big data characteristics, that volume, that velocity, the variety of data, big data types, so that unstructured data, structured data, semi-structured data. We talked about distributed computing, and how distributed computing enables us to process batch data and streaming data. Then we looked at artificial intelligence. We looked at machine learning. We looked at deep learning. We talked about data science, and we made sure to differentiate between those terms used interchangeably. We looked at roles on data science teams and talked about how data engineers and data analysts, data scientists, for example, work together on this data science workflow and what tools they need throughout the various stages of that workflow. We then moved into struggles that organizations face with big data and AI. And then we moved into Databricks and talked about how the Databricks Lakehouse Platform addresses all of those challenges, and also what it looks like in an organization. So what a workflow looks like using Databricks in an organization. If you have any questions, please let our TAs know. If not, stay safe. We hope you enjoy the rest of Data and AI Summit. And again, please let us know if you have any additional questions that we can help you with. Here's a few next steps. If you want a personalized consultation for how Databricks can help your organization specifically, please reach out to value@databricks.com. If you're curious about other Databricks customers and you want to look at some more success stories, please view our customer success story gallery at databricks.com/customers. You can also go to academy.databricks.com if you want to learn more about Databricks itself. Maybe if you want a more technical introduction to Databricks, maybe you want to try some of the hands-on features, or perhaps you know people on your data science team that might want to try out some of those features. Again, that's academy.databricks.com. Thank you so much for joining, and please make sure to fill out your evaluation when you're asked to do so. Have a great rest of Summit.